Welcome back, student, to part 2 of doing the line integrals. In this part, we will do example number 3. So if you haven't watched example number 1 and 2 in part 1, please pause this video, watch example 1 and 2, and then replay this video again. In example number 3, we again want to find the line integral, but the only difference between this example and example number 2, I don't have ds, I have it as dy. By the way, having it as dy, much easier than having it as ds. Now, remember, in the line integral, I will give you the line integral, the question, and I should give you the parameterization for c, which means x should be given in terms of t, y should be given in terms of t, but in this example, we don't have it. So the first step that we need to do here, we need to find the parameterization of c. That's the first step. Now, how do we proceed with this one? Again, I have only the equation that describes c is y equal x squared, and this is just one equation with two variables. In that case, one of them would be a free variable, so one of them I will have to call it t, and I find the other one. So I will call x to be t, and this is my free variable. The other one, which is y, will become t squared. Why it become t squared? Because remember it's t, so it will be just t squared. And finally, you need to tell what t from where to where. Of course, t is exactly x, and x is from 0 to pi. So this will be from 0 reaching pi. Now I have the parameterization, I have everything that I need to solve the question. So I will go now to step number 2, which is we evaluate the given line integral. So we evaluate this one, integral c xy squared plus sine x dy. Now, what's this line integral? Again, we have to do the integration from 0 to pi, because that's where the t is. Now you have to remove every occurrence of x, and we write t, so the first x will be t. Now, for the y, it will be, of course, y squared. It will be just t squared squared, and then we have the plus sine x. Instead of x, I will write t. And now, as the main issue here, what shall we replace dy with? Well, that is easier in this case, because what we replace with it will be just y prime, the derivative with respect to y, which is in this case, it will be 2t dt. Now, all what we need to do is simplify this integral, so it is from 0 to pi. Here we have t power 5, because you have t squared squared and another t, plus 2t sine t dt, which is the integral that we need to find. Now we need only to evaluate this integral using the idea that we have already seen in calculus 2. So this integral will be integral from 0 to pi t power 5 plus 2t sine t dt. Of course, this integral, we need to do it by integration by parts. So let me do it in a different color. This is integration by parts. It's a good time that we go ahead and evaluate this integral separately here somewhere in the page. So we'll do it integration by parts as we did it in calculus 2, and finally I will go ahead and we'll write the final answer here. This integral should be from 0 to pi. Let's go here and do the integration by part for the integral 2t sine t dt. Well, for integration by part, you need to write your function as u and dv. And why is that? Because later the integral u dv equal uv minus integral v du. Now what should be my u? Because I have two functions, one of them is polynomial, one of them is trigonometric. Usually the polynomial get more privilege to be u, so the polynomial will be just 2u. So here would be 2t. Second function will be sine t. Now you need to find du, which will become 2 dt, and you need to find v, which is the integration of sine, and this is just cosine. So my final integral will be minus 2t cosine t plus, and why there is a plus? Because I will do v du. I will multiply this by this, I got it here, and then minus v du, but there is a minus and a minus, so it will become a plus, integral of 2 cosine t dt. Now integral of 2 cosine t, that is something easy. We can find it as 2 sine t, and that will find for me this integral. All what you need to do is to take this one and you write it here in your final answer. So my final answer will be t power 5, this will be t6 over 6 minus 2t cosine t plus 2 sine t. One time I will evaluate with pi instead of t, one time I evaluated with 0. Let's see what we get. If we substitute pi, the first term will be pi power 6 over 6. If we substitute pi here and pi here, I will get cosine pi. If we multiply it by negative 2, this will be just plus 2 pi. If we substitute pi here, this will be just 0. Now, later I have to substitute every t by 0, and again everything will go away, and this is the final answer up here. So that's how we solve the line integral if we have dx or dy. Next example, which is example number 4, we need to evaluate the line integral. We have as a line integral, and here we have it as 3 variables, dx, dy, dz, and I have the line segment given to me. So again, all what we will do is we will find the parameterization, which means I will find x in terms of t, y in terms of t, and z in terms of t. And then I will replace every x by its value in t, every y by its value in t, every z by its value in t. And then I will replace every dx by derivative of x with respect to t, every y by derivative of y with respect to t, and every z by derivative of z with respect to t. And that's what we will get here. Okay, so what we are going to do here, let's go back here. First step, we need to find the parameterization of the curve C. Of course, here I don't have any equation about the curve C except it's a line segment. Now, for the line segment, we have an equation for the parameterization, and that equation is given by r of t equal 1 minus t, this is fixed, and then you multiply it by the vector representing the first point, and then plus t, and then you multiply it by the vector representing the second point. So we're assuming the line segment goes from the point r0 to the vector r0 to the vector r1, and remember t will be fixed between 0 and 1, and that's information that also I needed to be there. So this will be 1 minus t. Now the vector representing the first point will be 1, 0, 0 plus t, and then times the vector representing the second point, which is 4, 1, 2, and that's between, making t between 0 and 1. Now all what we need to do is we need to distribute the factor outside inside the vector. So we will get 1 minus t for the first component. If we multiply anything by 0, we'll just get zeros. Now the second one is 4t, t, 2t. Now we have to combine these two together. If we combine them together, what we will get is 1 plus 3t, comma, t, comma, 2t. So the parameterization that we reach at the end is x equal 1 plus 3t, y equal t, z equal 2t. In addition, the integral will go from 0 to 1. And that's how we find the parameterization for this curve. Of course, once we have the parameterization, evaluating the line integral become easier and more simpler and more focused. So that's exactly what we are going to do up next. So now what we will do is we replace every x by its value, every y by its value, and every z by its value. So let's go back to the integral and let's write it down, evaluate it at every point we need to evaluate. So the integral in the question was z squared dx plus x squared dy plus y squared dz. Just let me check that's exactly that's what it is. Now how we will evaluate it? Again, I will just replace t from 0 to 1. Now the first z, I put the value or the parameterization of z, which was 2t, times dx. I'll replace it with the derivative of x, which was 3. So I get this one. Plus, now the second part will be 1 plus 3t times the derivative of y. Now what was y in terms of t? It was just t. Y was just t, so it's perfect. Derivative will be just 1. Plus last one, z is 2t. Derivative of, last one I just have to replace y, so I replace y with t. And derivative of z is 2, finally, with dt. So this integral will become 0 to 1. This integral will become 12t squared plus. Now if we expand this one here, it will be 1 plus 6t plus 9t squared plus, if we expand this one here, we'll get 2t squared. Now we can take all the elements together. So t squared, 12 plus 9, 21. So this would be 23 t power 2 plus the coefficient for t is only 6t plus only 1 here dt, which is fairly easy. Integral, it will become 23 over 3t3 plus 3t squared plus t, substitute 0, substitute 1. The final answer will be 23 over 3 plus 4, which is, it will be 3 here, 35 over 5. And that's we will finish example number 4. So please watch example. The last type of line integrals will be in part 3 of this series, and in that part we will do a line integral for a vector field. Thank you for watching.